Get started. All right, welcome everybody. It's Saikat Guha. It's my pleasure to welcome you to the OSC Colloquium, and a real pleasure and honor to introduce my Ph.D. advisor, Yuen-Shapiro from MIT. When we asked Jeff to send this title, and he sent that for his talk, things that occurred to me that that Jeff was busy inventing squeeze states a year before I was born. So Jeff has done a lot of work on quantum communications, on some of the earliest work in squeeze states of light and its applications to optical communications, radar theory, and most recently in quantum information science and its applications to quantum optical communications, sensing, radar, and lots of applications that you are going to hear about in his talk today. Jeff has been at MIT for majority of his career, I believe, from his undergraduate days, majority of his life, starting from his undergraduate days. I mean, he was at Case Western University for 4 years, I believe, after his PhD from MIT as an assistant professor. And after that, he joined back MIT. He was an assistant professor, then associate professor, and associate department head, and then director of RLE for several years when I was his graduate student. And he is, I guess, on his way to close to retirement now at MIT. So he has spent all his life. So, and if you may not know, there's at least two more faculty members here, Zheshen Zhang and Chuntao Zhuang, who are postdoc and graduate students of Jeff. So it's a real pleasure to have him here to speak to us. So looking forward to your talk, Jeff.
Okay, thank you very much, Saikat. In fact, thank you. Thank you for inviting me here. It's actually a great honor for me to speak at the Optical Sciences Center, a world premier location for all things optical. And I'm going to tell you what I've been doing for the last 40 years. And not even complete. I mean, this is incomplete and only semi-chronological. So here's an outline. I'm going to start with quantum diffraction theory, talk some about photodetection, spontaneous parametric downconversion, which is being researched here. Leads us into some issues of phase-sensitive coherence. Those of you who know coherence theory may not know anything about this. One of my early, and only one of maybe two forays into quantum computation about quantum cross-phase modulation. And then there's a lot to do about quantum radar. This is the quantum illumination story. And then for the young people, there's plenty left to do. So let's start with quantum diffraction theory. And to get started, go to Carl Hellstrom's quantum optimum binary receiver. In the 1960s, lasers were now out there. People started worrying, Hellstrom in particular, if you're worried about optical communication and want to get to an ultimate quantum limit, what is the limit in binary decisions? So I don't know how much quantum mechanics you know, but we're choosing between is it a 0 or 1 being sent, and instead of probability distributions you'd have in classical communication, you have density operators. And so what Hellstrom worked out, if these hypotheses were equally likely, and you measured this abstraction and made that decision, you'd have this error probability, and that would be the best you could possibly do quantum mechanically. Because I don't know the audience well, I'm not going to try to dwell on details, but this was the best you could do quantum mechanically in an abstract sense. Where the hell do you get the density operators from? Well, Hellstrom talked about that too. He went to a textbook description of quantizing the electromagnetic field. If you look, and this is, I guess, where I learned a lot of this stuff. Actually, I had the earlier version of Louis Zell's book. The world said, well, you choose a volume of interest to you that encompasses the field that you care about over the space-time region of interest, and you quantize that field at the initial time. So Hellstrom pictured, all right, this receiver box is where I'm going to quantize. The light comes in, it's in that box. At some initial time, I do the quantization. I get density operators, and then I decide. Okay? Well, those of us who've ever thought about communications, optical or radio, say, you got to do a link budget. How much power do you need? How big are the antennas and all this stuff? So I knew about free space optics because I started in graduate school before Corning glass reached the breakthrough of 20 decibels per kilometer in optical fiber loss. So it was going to be through the air laser comm that was going to give us a lot more bandwidth. So here you've got line of sight propagation between the exit pupil of a transmitter and the entrance pupil of a receiver. And if it were vacuum, no atmospheric effects, and you ignore polarization or take linear polarization, and this is the field envelope as a function of space here and time, space here and time, transmitter, receiver. This is Fresnel diffraction. Okay, and you can do a link budget from that. How much power you transmit gets received. This is classical. How do you do it quantum mechanically? Well, this is the first thing I did quantum mechanically. I did it with Horace Yuen. It's the same line of sight propagation geometry. But now there are carets on top of these two fields that they are field operators now of quantum mechanical origin. And you can talk about their quantum states and figure out what happens. But it's the same Fresnel diffraction integral. There are a couple of extra caveats associated with preserving the Heisenberg uncertainty principle, preserving commutator brackets, that this integral now has to be not just over that pupil where you're sending light out, but over the entire plane here. So you have to include unexcited modes coming therefrom. And we're using a quasi-monochromatic assumption here to use this type of formula. So you really needed this before anyway, that the bandwidth is much smaller than the center frequency. K is omega naught over c, lambda is the wavelength. And the measurement, this is the field operator at the other end, we're going to limit that measurement to the receiver entrance pupil. That's the only place. The thing that propagates through that pupil is all that you can measure. We showed this in 1978. Horace Yuen went to doctoral program with me. We both had the same supervisor, and then we went away for a while and both came back to MIT. I didn't do quantum stuff. I learned it from him because he gave a talk saying, I've got a way of getting rid of all diffraction loss. And I said, that's great. I got to find out about that. And then we did this and found out it didn't work. Okay. But there's an important message about this, which resonates to this date, because this diffraction theory propagates arbitrary input states to tell you what the output state is like. And you can go look at papers, I think even coming out today, that have some propagation geometry, and they take some particular state, and then they labor to work what goes on at the other end, without realizing it could be done more conveniently this way. Well, so we can propagate states, at least through vacuum. You could worry about other propagation media. How do you detect interesting quantum states? Well, we typically do some kind of photodetection theory. And it turns out there are two theories of photodetection, semiclassical and quantum, and I want to tell you about them. This is the semiclassical theory. Almost ideal direct detection. Direct detection means the light field that you care about. Here, there's no caret. This is classical. This is the positive frequency field. This is the center frequency. This is a function of space on the detector plane and time, the envelope of that, linearly polarized. This is my detector. This is where the almost ideal part is coming in. This is the quantum efficiency of the detector. Now, I should tell you, semiclassical means you treat light as though it were a classical electromagnetic wave. It may be random, but it's classical. And it's quantum, it's semiclassical, because you say there is quantization. The electron charge is discrete. And therefore, at low light levels, the fundamental noise, even if your light is deterministic, is the shot noise effect. And so here we're saying I get a current out. I've made it ideal so that you're seeing discrete emissions of charge, instantaneous emissions of charge in response to a weak light field coming in as a function of time. And if I divide out the electron charge and integrate, then I get this staircase function. And the semiclassical theory of photodetection says if this light's deterministic, no randomness to it, these detection times form something called the inhomogeneous Poisson point process. This is a Poisson counting process. These sorts of processes are characterized by a rate, the average number of counts per second at a time t. It's the quantum efficiency, the short time average power, averaged over many carrier frequency cycles, but less than the bandwidth of that modulation, divided by the photon energy. And now, if I let you, you'd attack me, but you said the light was classical. Why are you counting photons? Why are you talking about photon energy? And the answer is, I could multiply in the electron charge and lump all of that stuff together and call it responsivity. We're just normalizing power in terms of joules, and you can do that. And this P of t, because I like to have these fields have photons per second per meter squared units for the magnitude squared, is given by this formula. This is a convenient way later to do the quantization. So this is, it would be an ideal detector. There's no dark counts, there's nothing else, there's no thermal noise, no random gain in it. Here's how you can characterize the statistics of that semiclassical model, two different ways. One is you can get the sample function density. If you've got some finite length of time, 0 to cap t out here someplace, you can point to the explicit times at which you get counts, and you get a joint probability density for the times of those counts and the number you get at the end of t seconds. And there's an alternative way to do that with something called the multi-coincidence rate, which says what's the probability per unit time of getting counts in a short interval at u1 to u1 plus delta t up to k, where all these times are between 0 and t. Let the delta t go to 0, so this becomes a rate. And that turns out to be, for semiclassical theory, for that Poisson theory, the product of the mu's at those times. So here is the sample function density. Here is the multi-coincidence rates. They're equivalent descriptions. This one is called exclusive probabilities, that one inclusive. Exclusive because this one says the only times at which you got counts were there. And this one says you have counts here, but you might have other counts too. And why do I bother with this? Because this is much more informative. It's because in the early days, the only quantum theory of photodetection coming out of sort of Roy Glauber's correlation function stuff was that you took, for that kth order multi-coincidence rate, you took the quantum efficiency to the kth power, did all these integrals over the area, and then you have this messy correlation function. This is the adjoint of that field operator. Okay? And that's the multi-coincidence rate. And because this is inclusive, where I'd rather have inclusive, you have to do this horrible set of Venn diagrams because you count too much probability at one level, then you subtract it out, then you add it more, and back and forth, and it would be a god-awful mess. Except that for laser light, that's the quantum version of coherence state, is the quantum version of ideal laser light. That's the quantum field that gives the Poisson model from the previous slide. The multi-coincidence rates become this simple form in terms of the classical field associated with the coherent state. And you can actually do all these sums and you get back to the other result. But it's a real pain to use it this way for other states. So in a later thing that Horace and I did, we came up with this representation theorem. Okay? It's still the almost ideal direct detection. But now we're putting the field operator in. You still have the same picture of discrete events in time and a counting process. And then we get this wonderful representation theorem that the photocurrent, this is a classical outcome waveform, the output of a quantum measurement, is equivalent to measuring this observable, the electron charge times the integral E dagger E. This is the photon flux density, E dagger E. And if you go to the counting process, this classical counting process has the same statistics as this operator measurement. And these primes indicate that we had to do something special to account for the loss associated with the quantum efficiency being less than 1. You have to put in some vacuum state noise. And this is really about commutator brackets. And what's important about this is it allowed us to get the quantum measurement representations for homodyne and heterodyne detection, the full space-time form. And you don't have to go through those multi-coincidence rates. Whoops. So now let's see. We understand something about propagation, at least however little quantum mechanics you've seen, at a high level of abstraction, that you can do something like diffraction of the classical type, but for quantum fields. And we see that you could do something like getting sample function densities for quantum states. You tell me the quantum state, we can go work out what the statistics are. Well, when do you ever need to do all the quantum stuff? It turns out we can discern two things. There are states of light for which the semi-classical and quantum theories give you exactly the same prediction statistics for heterodyne, homodyne direct detection. Those states are called classical states. Any experimenting involving classical states, linear optics, and any of those three basic photodetection paradigms, you'll get the same answer if you do classical stuff with shot noise, or if you do the quantum stuff. And that means that experiment can't distinguish between those two theories. We know the quantum theory is right and the other one's wrong. Okay? But those experiments can't distinguish them. So we need non-classical states. Classical states are almost everything. Sunlight, light bulb light, LED light, laser light, ... Non-classical states are States with definite number of photons, single photon state, 2, 3. Squeeze states, those of you who know what that is, some of you do. Entangled states, those of you know about entanglement, at least at some level. So we want to talk about generating some non-classical states. And a good way to do that is with spontaneous parametric downconversion. And this proves how much of a theorist I am. This is all you need to do. You sign a big blue arrow into a box that's got a second-order nonlinear crystal in it, and you get out signal and idler, weaker beams, in the red, because that's a longer wavelength. You didn't put any of them in, that's why it's spontaneous. It's parametric because this is a nonlinearity. It's downconversion because these are at a lower frequency than those. With a strong, non-depleting continuous pump at omega p, no inputs at the signal and idler frequencies, occasionally, this is a process of photon fission. Occasionally, a pumped photon splits into lower frequency, signal and idler. And to get anything out of this, you need to have, well, in nonlinear optics, where they didn't worry about the quantum stuff, they call it frequency matching. But if you multiply by h bar, this is energy conservation. This much energy is going to give you the energy of those two. And if the boldface k's are the wave vectors, the propagation vectors of the pump, signal, and idler, this is called phase matching in nonlinear optics. But at the photon fission interpretation, it's momentum conservation. Even with both of those obeyed, it's a fairly inefficient process. So how do people usually represent parametric, spontaneous parametric downconversion of this type? Well, let's assume it's type 2 phase matching, so the signal and idler are orthogonally polarized. Let's say it's in a waveguide, so I don't have to worry about spatial characteristics. And you do perturbation theory, because people like to do perturbation theory. Then you get this. Kappa is a nonlinear coupling coefficient. L is the length of the crystal. Delta K prime is the phase mismatch at detuning omega. This is how you get phase mismatch. The point is, this is a single signal photon at the frequency. I'm doing it frequency degeneracy. This is half the pump plus a detuning. This is half the pump minus a detuning. It says photons come out in pairs, one signal, one idler. Energy conservation says blue is that way. If one is blue detuned, the other is red detuned, the same amount. They're orthogonally polarized automatically. This is done post-selected because I've made some measurement and I've seen one signal and one idler. I've done spectroscopy on it so I can see the frequency. This is not normalizable. I mean, you do quantum statistics, you're supposed to have unit length kets. These are not unit length. And it neglects the fact that spontaneous parametric downconversion can give you multiple pairs. And especially neglects the fact that I'm running this in continuous time, CW pumping. You get a whole stream of these out. This is just one pair of photons. So how you should really do it is you should use coupled mode theory and realize that what you're getting out in continuous time is a jointly Gaussian state of signal signal and idler. Well, you know, I think many of you, about Gaussian noise or Gaussian random variables. First and second moments are all you need to know to work out the distribution of Gaussian stuff. And that's true quantum mechanically as it is classically. So the non-zero first and second moments of what you get from CW, type 2 phase match, frequency degenerate, spontaneous parametric downconversion are these two normally ordered, because it's E dagger E, correlation functions. This is the fluorescence spectrum of both the signal and the idler. And this unusual one, because there's no dagger, this is called a phase-sensitive cross-correlation function given here. This is spelled out in this paper. This is a very unusual kind of coherence. It's a phase-sensitive coherence. And I got to tell you about that, because you can go back to Baran and Parent's book. You can look at Mandel and Wolf and read about coherence theory. And they never talk about that type of correlation function. But we have to, because that's what parametric downconversion produces. So let's talk about it a little bit and then show how it's relevant to something called ghost imaging and imaging with undetected photons. Doesn't that sound interesting? Imaging with undetected photons? Not my idea. So phase-sensitive temporal cross-correlations. If you have a harmonic oscillator, simple harmonic motion, you can think of it as some complex number times this e to the minus j omega naught t, rotating around. And the real part of that I'm representing here. Think of this as a harmonic oscillator behavior. This is basically normalized versions of position and momentum. And do it for two of them, the signal and the idler, classical. And supposing I want to evaluate the correlation function between these two real-valued signal and idler simple harmonic motions. You do a little magical stuff. And remember, I'm using angle brackets both for quantum mechanical average, well, I haven't said it before, and classical averages. You get two different terms, one of which only depends on the time difference, and that's the phase insensitive term. This conjugate takes the classical role of the adjoint dagger in quantum mechanics. And I call it phase insensitive because supposing I shift AI and AS by theta, by the same phase, AS conjugate AI doesn't change. This other term doesn't have the conjugate. I call it phase sensitive because if I change both of these by a phase shift theta, it does change. It changes by 2 theta. And a real consequence of interest is that this depends not only on the time difference, but also on the absolute time at twice the frequency. And those of you who know about squeeze states realize that's what squeeze states do. There's a low noise quadrature and a high noise quadrature, and they swap back and forth at twice the speed of the center frequency. Well, you can go through some inequalities, they're just Schwartz inequalities, and show that the magnitude squared of the phase insensitive cross correlation has this upper limit. The magnitude squared of the phase sensitive cross correlation has the same upper limit. And now you can go to quantum mechanics. Now I got quantum harmonic oscillators. A single mode of the electromagnetic field is a quantum harmonic oscillator. We get the same breakdown, except these are operator correlation functions. And you find that the normally ordered one obeys the classical condition, but the phase sensitive one doesn't. And in fact, this upper limit is higher than that one. That's a non-classical correlation. And it turns out you can get to this upper limit for the output of spontaneous parametric downconversion. And that's very important. So let me tell you some of the differences about phase-sensitive coherence. This is spatial coherence, and this is autocorrelations. Imagine I have a source over here that has some correlation length, rho 0, and has some size, intensity size, A0. It's a partially coherent source. So this is smaller A0 than rho 0. Then the light sprays out larger than the diffraction limit, and there's some degree of growth of coherence. And what I'm showing here, and this is important about the growth of coherence, this light propagating in this direction is correlated with things within that cone, light in this direction with this cone, light in this direction with this cone. And this is very familiar if anyone's done partial coherence before, the Van Sittert-Zernike theorem for an incoherent source. This is the same thing. There's a coherence length, rho 0, and there's a larger size of the source, A0, except this has got phase-sensitive coherence. So the light sprays out broader, but the light in this red line is correlated with the stuff in this red cone. The light in this green line direction is very unlike normal coherence theory. Okay, not written up in any of the standard coherence books. All right, well, who cares? Well, there was this experiment done by Yuen-Shapiro group in 1995 where a parametric downconverter here created signal and idler beams. The signal went through a filter and then an aperture. If you're at University of Maryland, Baltimore County, what do you think you put on your aperture? MIT, right? No, sorry. They put at UMBC, appropriate. So, and then they had a big collection lens, and this detector, it's a photon counting detector, is just trying to collect all the light it can. No spatial resolution here. The other direction, because signal and idler are orthogonally polarized, the other direction went this way. And now there's, again, with some narrowband filtering. And then they had a scanning fiber probe, so this moved around, and the single photon detector. And now the point is this has a lot of spatial resolution. But there's no object here. There's no object information in the counts you get here as you scan that probe around. There's no object information here in this what's called a bucket detector because it had no spatial resolution. But if they do some coincidence counting and a little thresholding, they get UMBC. And they called it a ghost image because you can read the words. And moreover, they said this is a quantum effect because we started with entanglement. And assuredly, if you listened to me earlier, you would agree that because they started with an entangled state, I couldn't get the statistics right using semiclassical theory. So this is a quantum image. But later, that same group, now Scarcilli in the lead, used pseudo-thermal light, by which they called it, this is a figure directly from the paper, a chaotic source. But what it really was a laser, CW laser, shining on a rotating ground glass to make it spatially incoherent, but time varying slow enough to be resolved. Then they use a beam splitter. They went through a two-slit pattern onto this bucket detector. They went the other direction to the scanning probe. They did cross-correlation, and they could recover a ghost image. Now, the UMBC group said, all right, it's still a quantum image. It's due to non-local two-photon interference. And they said it's not just the fact that there are correlated speckle patterns being cast by this source. I had a doctoral student got involved looking at this. And what we did, this is his work through here and then my work through there. We looked at the downconversion case. So this is a model of exactly what's in the first Xi experiment I showed you. And then we looked at the rotating ground glass. This is exactly our model for what they did in the second experiment. And we used that Gaussian-state theory that I showed you for what comes out of a downconverter. We could explain all of this. We could explain all of this. We could tell you, because this is using phase-sensitive coherence, that the image is inverted, but this one isn't, and all that sort of stuff. And then we had arguments with the UMBC group. And then I said, well, look, this was just having correlated speckle patterns. Why not, instead of doing a, this is the right one. Instead of using rotating ground glass, why don't I just put a spatial light modulator there and create patterns, okay, like it gets done in compressed sensing. And you can do that, and that works in principle. And we did some experiments later on that. And I said, well, why do I even need this reference pattern? If I'm putting programming patterns in here, I just compute what it is. And this is a computational ghost imager. And I thought that settled the argument about non-local two-photon interference, because now there's only one photon. I mean, there's only one beam. So that was all interesting. And people are doing tremendous things with ghost imaging now, lots of interest still in it, and most of it is computational. Then there's this paper, much more recent. This is from Zeilinger's group. It's in Nature. This is figure and results from their paper. This is quantum imaging with undetected photons. So here comes a pump beam, and it goes through a downconverter crystal and creates longer wavelength beams, the signal and the idler. And the idler's longer wavelength, that's the color coding would suggest. The idler goes through an object transparency and then gets into another downconverter crystal, except now this is not spontaneous because this idler is going through there. And then we pump that one. And then the signal continues this way, and this way we have a dichroic that throws away this idler wavelength and takes the signal out, because this converts some of the idler into signal, and then you have an interferometer here. And okay, if you're going to do some sort of quantum thing, magical, what shape are you going to use for that? Yeah, you're going to use Schrodinger's cat. Oh, by the way, I should tell you, the first experiment on computational ghost imaging, before we got to do it in my group, a group at Weitzman did it, and they told me about it, and they let me show their sort of movie of building it up at a ceremony at which I was getting an award, and I was giving an invited talk. What do you think they used? A ghost. Well, anyway, one of these, if you look at one of them, you can get a positive image. You look at the other one, you get a negative image. If you add them, you get nothing. If you subtract them, you get a cleaned up version of the positive image. Nice. So why is it quantum imaging? Well, it should be. They're generating non-classical light here. Why is it imaging with undetected photons? Because they're not detecting any of the red light photons, and those are the only ones that interacted with this object. And what can I say? That's the way it is. In fact, they did experiments where this object would be opaque at that wavelength. And that's neat. So I thought with my group that it wasn't really about the entanglement. It was about phase-sensitive cross-correlation as manipulated and created with these devices. So we did, I couldn't do the color coding the way they did. We had a signal idler source. And for analysis, we discretized in space, we discretized in time. And we looked at the case where this was entangled. It had a quantum-limited phase-sensitive cross-correlation between signal idler, or a classical one, which was at the upper limit set by classical physics, but otherwise was the same. The idler, the longer wavelength, goes through the object. We go through a phase conjugator, which can be described classically. It's that same setup as in the Zeilinger experiment. And we take the longer wavelength out. We dump the other one. I didn't show it here. We bring the signal back, and the idler, we do the two cameras. And what do we find? Well, it was MIT, so we did a simulation. The experiment would have been too hard to do with our resources. These are the strengths of the quantum and the classical cases, and this is the number of modes, I guess, in this. And the T was magnitude squared. M had 1/2. I had I over 2. And the T had minus 1/2. And all the other pixels transmitted 0. And this is the positive image. This is the negative image. This is the difference image for the simulation of the classical imager. And we've evaluated theoretically the signal-to-noise ratios. And for the classical image, it's lousy for either of these two, and you can see that. For the quantum version with the quantum source, it's even lousier. We didn't simulate it for the M and the T. The I doesn't give you anything because it's an interferometer, and it is sensing the real quadrature, so it wouldn't see that imaginary term. And the signal-to-noise ratio was much higher for the classical version than for the quantum version. So the magical stuff here is really about phase-sensitive cross-correlation rather than quantum per se. So let's talk about another type of thing, quantum mechanical. It's a quantum computation example. Oh, this is a motherhood slide, right? Optics is great stuff. You can get high-quality single-rail and dual-rail bases to do quantum computation, like the H and V polarized single photon states on a single spatial mode, or co-polarized single photon states on 2 spatial modes. And you can use wave plates and polarizing beam splitters and go back and forth if something's easier in single rail or double rail. That's not a big problem. And optical qubits are quick, low-loss, short-distance routing. I mean, you send it down an optical fiber. It goes from here to there at the speed of light. Well, 2/3 the speed of light. Free space interconnects. You can do single qubit rotations in single rail logic with wave plates. If you want to do the circuit model of quantum computation, get it all optical, deterministic, fast, convenient, room temperature even, you need scalable 2-qubit gates to complete the universal gate set. Now, of course, and there are people here looking and elsewhere very hard at all optical quantum computation, not thinking so much about this, or there's still some work saying if we could get that, and maybe we could get it this way. So when Isaac Chuang was a doctoral student in Yamamoto's group, they made the following suggestion. There is a cross-phase modulation, a cross-Kerr effect. If I put in a signal beam and a probe beam, here I'm showing their annihilation operators for whatever the spatio-temporal mode was, that goes into a cross-Kerr effect. Then the probe beam, by its photon number in their model, can put a phase shift on the signal beam, and the signal beam will put a phase shift on the probe beam. And they're neglecting loss and neglecting dispersion and neglecting self-phase modulation. But if you could do that, and you could make that nonlinearity strong enough that a single photon from the probe could put a pi radian phase shift on the signal, and conversely, a single photon in the signal could put a pi radian phase shift on the probe, then this arrangement, calling this control and target in two-rail logic, dual-rail logic, gives you a C-phase gate. And that's enough to complete the gate set. Or you could convert it with a couple of beam splitters into a C0 gate if that's what you prefer. And that would be great. Well, it was known then, it's still known, that we don't have a good, shine it through a box and get a pi radian phase shift. In fact, then, and in many ways now, it's still fibrous Kerr nonlinearity is the most appropriate. Now, people had talked about Kerr effect for generating squeezing, and so I'd already encountered when I ended up doing some work with Hewlett-Packard Labs that there's something funny going on by putting this up here, because the Kerr effect is not driven by photon number, even multiplying in by h bar omega and making it joules. It's driven by watts per meter squared. So if I'm in fiber, I can give you the meter squared as the core area, but to get to watts, I need a length of time to get to joules. And what should that be? So I wanted to look at this thing in continuous time. So here I'm drawing the same thing, except now I have field operators. I'm in single mode fiber. I'm not worried about the spatial effects. I got an A and a B, and now I'm going to have a phase shift And I'm putting this in because even though the Kerr effect in optical fiber is very fast, femtosecond speed, it can't be instantaneous. And it ought to be causal. So I need a causal impulse response here. And I've normalized it so I can have a coefficient out here. This is the phase shift. So the phase shift on K, viewed quantum mechanically, comes from the photon number on J, the other mode, through this fast but non-instantaneous phase shift. And in order to preserve the commutator brackets, to preserve that this field going into the fiber has the same commutators, the same Heisenberg uncertainty principle conveyed to the output, I need this sort of phase noise term added there. And I'm neglecting dispersion, I'm neglecting self-phase modulation, I'm neglecting loss, because I don't think, at the time we were doing this work, that they're going to help. If you can't make this work this way, you're not going to get it to work other ways. So the response function we showed couldn't be instantaneous, because if I use laser light and said it was instantaneous, this would imply, I don't know that people do pulse compression here, but lots of people make shorter pulses by chirping with self-phase modulation and then compressing. Nothing happens. So this can't be instantaneous, and it must be causal. And then the Kramers-Kronig relation gives you a result for the phase noise in terms of the imaginary part of the Fourier transform of that response function. And the question is, let's assume we can make kappa strong enough that you would get a pi radian phase shift from a single photon, and see whether or not optics-based quantum computation of the type suggested by Chuang and Yamamoto will work. And so it's the same diagram from before, from Chuang and Yamamoto, except they have continuous time fields going in and coming out. And I'm going to take as my input states for A and B as some weighted sum of 0 and 1, the basis cats, where 0 is vacuum and 1 is some wave function times a photon at time t. And this, of course, is normalized. And we'll make the peak single photon phase shift pi radians. And there are two places you could be that this waveform is much slower than h of t. This is a fast response time. Or conversely, this is much faster than that. It's a slow response time. And I'm not going to show you the details except to say it doesn't work. You don't get a high fidelity gate. This is not going to work. And people have done a lot of follow-on work on this. My group has done some. But there are some suggestions involving cavities, dynamically controlled cavities, atomic systems, and other things. But it's still not completely clear to me, anyway, that we have a complete solution to this. It's known that if you take light and load it into atoms or load them into ions, you can do the gate and then you can read them out. But we're looking here for something that you more or less put light in, it stays light and propagates through a medium and comes out okay with either a cavity or no cavity or a set of cavities. So that's the end of that foray. And let me get to the last story I want to tell you. I have a longer version of this story. It's very interesting because there's tremendous amount of tumult, I think, in the defense community every time, particularly people from China, talk about quantum radar. And I get a lot of calls about this. So let me tell you the story. I gave an invited talk at a conference in Israel earlier, a month ago. And it was a conference I ordinarily don't go to. It was an RF circuits and maybe a little bit of radar conference. But they had a special session on quantum radar, and I gave this talk. And I began, thank you for inviting me. I'm going to tell you the quantum illumination story. It is a cautionary tale, so keep that in mind. This is the start. Seth Lloyd, my colleague, coined the term quantum illumination in this wonderful article in Science. Here's the abstract. And I'll just highlight the key statement. Quantum illumination with m bits of entanglement can increase effective signal-to-noise ratio by a factor of 2 to the m. That gets very big. And remember, in error probabilities, the signal-to-noise ratio shows up in an exponent. Wow. Well, some of us didn't believe it, and I read his paper very carefully, and I decided it was right. But still, we didn't believe it, because he makes some assumptions. And then later, he and I realized that when you put those assumptions under close scrutiny, we extend Lloyd's analysis to full multi-photon input Hilbert space, blah, blah, blah. Oops. You read it already. I think when I gave a slide like this in Israel, on the bottom I said, is this the end of the quantum illumination story? And so this is about the third slide in, and I had a 30-minute time slot. So I said, no, it isn't. Because, remember, Seth's paper was published in 2008. This is published in 2009. But in 2008, that's the reference will appear eventually below, Seth's doctoral student, Siwi Tan, and a variety of us, some of whom are in the room besides me, at least one of his, decided to look really at laser light, laser radar versus this entangled radar. So here's the laser radar. You send out laser light, coherent states. It's interrogating this region. Is there a target? Yes or no, equally likely. And you get some return light back, and you do a measurement and try to decide to make minimum error probability. I'm not going to read you all this stuff about what it means in terms of the model. I'm just going to say, look at the red. This is the error probability of this coherent state system. It's e to the minus m. M is the number of independent temporal modes. It's a time bandwidth product. You're sending out a pulse of this length, and it's got duration t, and it's got bandwidth w. Tw is much greater than 1. Time bandwidth product, like radar people talk about. Ns is the average number of signal photons per mode. Kappa is the round trip loss, or transmissivity, really. Nb is the average number of background photons per mode. Just look at the form of that. That's the effective signal-to-noise ratio in the exponent. This is the quantum illumination of Tan et al., a spontaneous parametric downconverter. You're sending out the signal and keeping the idler. You're doing it. I'm only showing one mode here, one mode there. It's still otherwise the same setup, equally likely, absent or present. All these things are basically the same, but including that we're using a very large number of modes. This is the error probability for the quantum illumination. It looks a lot like that one up here, except the factor of 4 isn't present. Okay, so now from an exponential improvement, and this thing is not susceptible to the problems that I showed with Seth on the previous slide. So this is a real improvement under ideal circumstances, a factor of 4, 6 decibels in signal to noise. But it's up in the exponent, so it could be a big deal in error probability. Now, there was a problem in this paper. The paper was not wrong in any way. And we gave some oral presentations. See, we gave a conference paper, and I made presentations at sponsor briefings. And we always got asked, well, how do you make the measurement? And like I said earlier, we don't know. These come out of what are called quantum Chernoff bounds. They tell you this is the performance. They don't tell you how to get it in any easy way. You could write down, something in terms of density operators and so forth. But what we knew was, the reason for this is that there is a stronger than classical cross-correlation between the signal and idler, that phase-sensitive cross-correlation. And even though, and this is the important thing about Seth's original paper, he got a performance improvement even though he's using entanglement, even though entanglement was destroyed by the loss in noise. That's true here too. But if you send out, and these are sending out the same energy, for the same energy transmitted and saving some other beam with which this one was correlated, you can't get a stronger correlation between these two using classical resources as you get using the downconverter. You start out with a stronger cross-correlation than classical will get. For the same transmitted energies, there's nothing going to give you a stronger cross-correlation there. So it had to be a phase-sensitive cross-correlation, and we didn't know how to measure that. But a very smart person, or two of them that I knew well at the time, realized that if I use a low-gain optical parametric amplifier, and I put in the idler that I have stored, this is the nth mode, you do this for all the different modes, and the return mode, the output from the amplifier is going to have that dagger that you want. Because a regular interferometer measures an A dagger A cross-correlation. And so if you just did photon counting on all the modes that come out, having done this low-gain parametric amplifier, and you optimize the gain of that amplifier, you get an error probability like this under ideal circumstances. Well, there would have been a 4 there for the classical system, for the laser radar. Nothing there for the ideal quantum illumination, but this is now a 3 dB improvement. All right, but it is a real improvement. And in fact, if you pull in some other papers, even papers that preceded this work, you could show that because this is what's called a mixed state discrimination problem, no local operations type receiver, and that's what this is because it does mode by mode processing, could get the full performance advantage. And what is needed is a collective measurement, measures all the modes in some coherent fashion together. And you could do that with something called a sure transformation on a quantum computer. So we could wait for the big quantum computer to have that available. But it would be nice to have something simpler. I should have put simpler in italics for reasons you'll see on the next slide. So here's the something simpler. This was done by another very smart person. It said what you want to do is you want to go through multiple cycles, and this is what a cycle looks like. Maybe 30 or 40 of them, where these are all annihilation operators, these are beam splitters, these are squeezers, this is some frequency generation, there's photodetection measurements, there's feed forward, and if you do this all right, it was shown that you could get to the optimum performance. And by the way, these are all working losslessly at the single photon level. We don't have that. But it was an in-principle thing, and it does lead to some other results that are interesting. But there was an experiment. I think this is the only true experiment. There are people publishing things or submitting things now and calling it quantum illumination that violate the fundamental precept of that Tan et al. Paper, in which it was shown that that quantum illumination system will beat any classical radar. That means it sends out classical light of the same transmitted energy. Okay. So here is a tabletop experiment done with a laser and a noise generator, because we had to insert noise, and a homodyne receiver. And here's a quantum illumination with a laser pumping a down converter and a lot of other stuff, and the noise injection, and a parametric amplifier receiver, and all this stuff. And I'm not going to walk you through it. But there's someone in this room who could, if you need to be walked through it. And what was found was we measured signal-to-noise ratio, and the classical illumination was like this, and the quantum illumination was like that as a function of the round-trip transmissivity, the loss. And one particular figure here, that there was a 20% improvement in that signal-to-noise, even though at this measurement point there was 14 dB of loss, and the noise was 75 decibels stronger than the return signal. So it verifies the principle. But remember, Seth Lloyd started out with this much improvement, and then it came down to 6 dB, and then OPA receiver got it down to 3 dB, and on a tabletop, it's now down with a very good experimentalist to 20%. All right, but it's worse than that. I'm sorry. You have no idea how many defense contractors. This is being taped, isn't it? I'm sorry, I shouldn't say that. I signed a release, for this. I'm going to be very. Oh, I'm retiring anyway.
I don't know if you know, this is going to be on YouTube.
I've been on YouTube before. And believe me, Lori Loughlin's daughter has much more following than I do. Anyway, for QI to offer any advantage, you need a low brightness signal. Average photon number per mode very small compared to 1. High brightness background. Average photon number per mode much greater than 1. And high time bandwidth product. High brightness background is not present at optical wavelengths. You may think the bright blue sky you see outside in this beautiful day is very, very high brightness, but if you go to a single spatio-temporal polarization mode, it's a small fraction of a photon. Oops. But at microwave, it's bright, so we should do microwave for QI. And even better, microwave is where people really care about radar and target detection and increasing sensitivity. And in fact, there was a paper that excited lots of interest. I said, well, look, we can use electro-optical mechanical converters to create a microwave signal entangled in the sense we want with an optical idler. We'll send out the microwave to interrogate that region where there may or may not be something. We'll get back a microwave. We'll use another converter to convert that in effect to optical and do detection. This is realizing an alternative to the OPA receiver called the phase conjugate receiver, but it has the same performance. And this is a diagram, a notion about what this electro-optical mechanical converter looks like. And then there was some hype. I'm a co-author of that paper, but I assure you I was not responsible for what led to this. And this still reverberates. Go get I believe it's a September 2019 issue of Optics and Photonics News. There's an article about quantum sensing. Somewhere in it, they mention Seth Lloyd's quantum illumination paper. Well, at least they don't talk about exponential improvement. And then they have this picture, and I think the caption says something about, well, maybe not quite this, but almost as bad. So now I'm going to come to the end of the story for this. For QI anyway. The longer version exists elsewhere, but it's not advantageous at optical frequencies because the background is low brightness. it's not advantageous, particularly at microwave frequencies, because you need a very large time bandwidth product to get a high enough signal-to-noise ratio so you get a meaningful error probability or receiver operating characteristic. And it's just very hard to get what you can get optically. At optical frequencies, at 1 micron wavelength, that's 300 terahertz, a 1 terahertz bandwidth and a microsecond pulse is a time bandwidth product of 1,000,000. Okay, to get that kind of time bandwidth product in the microwave with reasonable pulse durations is out of the question. So optical QI has the single, well, they all have the optimum QI has a single resolution bin interrogation. You can't split that stored idler. You have to use all of it for whatever bin you want to look at. Range, azimuth, elevation, Doppler if there's Doppler, polarization. Because if you split, it's like putting loss in. And that puts a loss factor into that exponent. So if you had 6 dB gain, if you had the ideal receiver for 1 bin, if you split it in 2, you only get 3 dB gain. If you have split it in 4, you have no gain. You know what radars do? They send out a pulse and they measure versus time and they figure out where the damn object is. Well, you can't do that here. And moreover, idler storage is a big problem. For an optical idler, the best choice is an optical fiber. And optical fiber is such that the OPA receiver loses its effectiveness beyond 11.25 kilometers. And if you had a perfect optimum receiver, it gets you to 22.5. And by the way, every so often I hear a meeting and somebody says they've got a terahertz bandwidth quantum memory. And I say, I got to find out about that. That's what I need. And then I find out what they're doing is they're storing a transform-limited picosecond pulse. That's not what I want. I want this huge terahertz bandwidth thing of microsecond duration stored, maybe. So there is a meta lesson, and it's important, even though this seems like maybe the end of the story. This is the first real example. Maybe it doesn't have any real utility, but the experiment shows that it is real. That entanglement can be beneficial when used in a scenario that breaks the entanglement in this bosonic setting. And that's a first. I'm almost done. Maybe I went too fast. Well, I only have maybe a couple more slides. I think there's a lot left to do, and I'm just going to mention a couple of things that my group has done fairly recently. And I know from talking particularly to Saikart about what he's doing, and Chun Tao, what he's doing, and Cheshen, and Bulat, that there are a lot of things happening here. So anyone who's thinking of moving into quantum optical communication, quantum sensing, don't worry that there will not be a good Ph.D. thesis, be it experiment or theory, or both. So recent examples from my group. Oh, I think you've all heard of quantum key distribution. Quantum key distribution actually predates Shor's algorithm, which breaks the RSA infrastructure for the internet. And the ideal for quantum key distribution is to be able to create secret keys securely between distant users, but create it at a sufficiently high rate that you use them as one-time pads. A one-time pad is a completely random string of bits. If you take your string of bits that you want to send and you do modulo 2 addition and you send that out, modulo 2 addition of a completely random string with anything is another completely random string. And it comes to the receiver, and that person adds in the exact same string, and now the associativity of addition, even modulo 2, recovers the message. The eavesdropper, who is always named Eve, which bothers me because my granddaughter's named Eve, my mother was named Eve, and why should this evil person have that name? Anyway, Eve, it's tradition. Eve doesn't have the one-time pad, can't get anything out of that. Well, that would be nice. Information theoretic secure transmission. Bennett-Broussard 1984 is the, to date, it's the first such protocol for quantum key distribution. It's still the preeminent one. Currently, the secret key rates you get with it are megabit per second class at metropolitan area distances on fiber. And of course, it could be worse at longer distances. And there are people working on quantum repeaters and all sorts of other things. But still, at metropolitan area distances, we're sort of megabit per second. And therefore, perhaps not fast enough. We want to send huge files to build up one-time pads. So they're used to rekey classical crypto systems, which means that your QKD is only as good as the classical crypto system. That may not be a problem because if you rekey constantly and the messages you're sending only need to remain secret for some finite length of time, then by the time someone has broken it, it'd be okay. But if you're some agency or commercial entity or who knows what that wants to keep it secret forever, then this is not good enough. So there's something called floodlight quantum key distribution, came out of my group. It's an intellectual grandchild, how about that for a phrase, of QI target detection. Because I realized that the problem with QI target detection optically, even if we solved the idler storage loss problem, was that the background wasn't bright. But if I thought about communication, I could put in a bright background, and I showed that you could do perfectly secure communication against a passive eavesdropper, somebody who's only listening to the light flowing in the channel. And then we had to extend that work beyond there. But still, it was not as good as it could be. And this floodlight, so if the downconverter-based passive eavesdropping immunity was the child, this is the intellectual grandchild. This thing, we've shown, enables gigabit per second secret key rates over the metropolitan area distance fiber connections, making one-time paired encryption possible. And we've done a tabletop demonstration with 10 dB loss. We have security proof that's not all the way up to absolute highest level, but it's still being worked on a bit. And it's interesting. Oh, no. Supposing the adversary, Eve, the nefarious Eve, has bribed the code clerk and has your crypto system's decryption. Even if it's a one-time paired, if Eve has the one-time paired key, well, she's got your message. Oh. But very recently, this is this year, we come up with low probability of intercept, a quantum low probability of intercept. It's an intellectual great-grandchild because it's this thing repurposed. And it enables Eve, and I don't know of any other system. I mean, there are alternative approaches to floodlight for doing quantum key distribution, maybe not with gigabit per second secret key rates, but maybe with ultimate level security proofs and experimental demonstrations on deployed fibers and networks being built in China and so forth. This is the only thing we know. Low probability of intercept means that the other party can't get it. And this has been done in military communications since Second World War, like frequency hopping and direct sequence scrambling. But this is a quantum one, so that even if Eve has your key, she can't get a good copy of the ciphertext. Regular LPI, like frequency hopping, has its own key. So if Eve can bribe the code clerk and get the one-time paired key or whatever key for the crypto system, why not get the key for the frequency hopping? But this is quantum. We think it will work over metropolitan area distances, just like this does, at gigabit per second rates. And by the way, I try to keep a reasonable number of lines here. These don't need the development of any new technology. So it's very interesting. So anyway, I got to acknowledge some people someplace. I think that's the last slide. I don't think I've published a paper since I've written up this slide. So the total of my co-authors on quantum papers is 122. I'm not going to list them all. This is a semi-chronological short list of most of the most important people. All right, that's still too long. And here's whose work I talked about today. And there's one more bullet. And these are the people on your faculty. So thank you for listening to me.